In this video, we will see in detail Balmer series which is observed in the emission spectrum of hydrogen and what makes it distinct from other series that we observe in the line spectrum of hydrogen. For this, let us consider a case where the hydrogen gas is filled inside a glass tubing that contains two electrodes across which a high potential difference is maintained and hydrogen gas is maintained at a very low pressure. In these conditions, electric discharge will take place across the hydrogen gas, due to which the hydrogen gas will be dissociated to give hydrogen atoms. And since the hydrogen atom takes up the energy in the form of electricity, the hydrogen will be excited. As we know, the hydrogen consists of a proton in the nucleus surrounded by an orbit which contains one electron. Once this electron takes up the energy, it will be excited from the first orbit to second, third, fourth, or a higher orbit. Here I have represented n is equal to 1 because initially the electron is present in the first orbit. That represents its principal quantum number. So the value of n, 2, 3, 4, 5, 6, accordingly the radius of the orbit also goes on increasing and the energy of the electron also goes on increasing as it possesses a higher and higher orbit. But when this electron is absorbing a higher energy, it will be promoted to a higher orbit. If it is absorbing lower energy, it will be promoted to a lower orbit. But once it attains an extra energy with it, it's no longer stable. That is the law of the universe. So, in order to stabilize whatever excess energy this particular electron has gained, it should shed it out. It should shed that excess energy. How can it lose that excess energy? It will lose that excess energy by emitting in the form of electromagnetic radiations. So, when you take hydrogen atom, which is in an excited state, to get the stability, you can expect the electrons which are excited in different hydrogen atoms. Why I am using different hydrogen atoms? Because each hydrogen atom contains only one electron. So, in all these hydrogen atoms, all the excited electrons, depending upon whichever higher orbit it is staying, to get better stability, it will lose the energy by emitting the excess energy in the form of electromagnetic radiations. So what happens? Sometimes the electron that is present in the sixth orbit, it may jump to 5, sometimes it may jump to 1, sometimes it may jump to 3, depending upon how much amount of energy it is going to emit. Or sometimes the electron which is going to stay in this orbit 3, after falling from 5, again it will lose energy and it will come to 1. So all types of transitions of electrons can happen across the various orbits that are present around the nucleus. Now, our topic of discussion is the Balmer series. So what Balmer did was, among the different types of electromagnetic radiations which were emitted, he observed that those electromagnetic radiations which were emitted in the visible range, So we should know which are the electromagnetic radiations which are emitted in the visible range from an excited hydrogen atom. They are red with wave number 1524 centimeter inverse, green with wave number of 2057 centimeter inverse, blue with a wave number of 2304 centimeter inverse, and violet with a wave number of 2439 centimeter inverse. So Balmer observed that these electromagnetic radiations which are emitted by the electrons from an excited hydrogen atom, they followed his equation. So what was his equation? Or it satisfied his equation. These wave numbers satisfied his equation. So what was his equation? His equation was, he predicted that the wave number of these electromagnetic radiations which falls within the visible range will be equal to, we indicate the wave number by nu bar, that is equal to 109677 multiplied by 1 by 2 squared minus 1 by n squared. So here, when the value of n is substituted as 3, the equation will be modified as 109677 into 1 by 2 squared minus 1 by 3 squared, or that will be equal to 109677 into 1 by 4 minus 1 by 9. If you work this out, you will see that the value is equal to 1523 centimeter inverse. You can see that over here. Like that, he substituted the value for n to be equal to next as 4 value. He substituted the value of n to be 4 here. So it becomes 1 divided by 4 squared, it becomes, or 1 by 16, and he got the value of 2056 centimeter inverse, which correlated with the wave number of green light. Likewise, he substituted the value of 5 for the value of n, so it is 1 by 25. Again he calculated and he got the value equal to 2303 centimeter inverse, which corresponds to the blue colored light with a wave number of 2304 centimeter inverse. Finally, he gave the value of 6 for n, and he observed that the wave number 2437 centimeter inverse corresponding to the violet color was being obtained. So his observation that the wave numbers corresponding to the visible regions of the electromagnetic radiations which are emitted by an excited hydrogen atom, it satisfies his equation wherein he had put the value of n is equal to 3, 4, 5 and 6. So these electromagnetic radiations which were falling within the visible region, they were named after the great scientist Balmer. So what's happening over here, if we can analyze, we can see that when the radiations fall from this, we are taking it up as the basic orbit. So when an electron, excited electron, falls from 3 to 2, red light is emitted. When it falls from 4 to 2, green light is emitted. When it falls from 5 to 2, blue light is emitted. When it falls from 6 to 2, the violet color is emitted. We are able to give this explanation based upon Balmer's equation, because Balmer has substituted the value of 3, 4, 5 and 6 for n. He put this value as constant because we see that 109677 multiplied by 1 by 2 squared minus 1 by n squared. So this 2 he made it constant, this 2 he made it constant. The value of n is substituted 3, 4, 5, 6. Accordingly, he got 1523, 2056, 2303 and 2437. So here lies the beauty of the Balmer's equation, and so these visible colors which were obtained from the emitted radiations of the hydrogen atom, they were named as Balmer series. In this context, we should also know what are the other series. Other series are Lyman series, wherein all the electromagnetic radiations resulting from the emission of the electrons which are falling from a higher energy level to the first orbit is considered, taken into account. Lyman identified it. So these series of electromagnetic radiation, you call them as Lyman series. N is equal to 2, we have already seen, that is Balmer series. Likewise, all the electromagnetic radiations which are emitted by the electrons when they fall from excited state to the principal quantum number value equal to 3, you call them as Paschen series, Paschen series. And where the electronic transitions happens to the fourth orbit, or when the principal quantum number value n is equal to 4, you call them as bracket series. And finally, lot of still more radiations are there, but these are the 5 ones routinely being studied, and this comes as bracket series. And when you consider the electromagnetic radiations which are emitted when n is equal to 5, that means electrons come back to 5, that is called as Fund series, PFUND series. But among all these series, the speciality of the Balmer series was that he could give an explanation for the wave number of these electromagnetic radiations which are in the visible range, which can be detected with our naked human eye. Because all the other series of radiations, Lyman series or Paschen series or bracket series or P-Fund series, you cannot distinguish them with your eyes, because the Lyman series, if you see, it belongs to the ultraviolet region. Other series, if you see, it belongs to several other radiations like IR radiations or microwaves. Such radiations, you cannot detect them with your naked eyes. So here lies the speciality of the Balmer series, that is emitted by the excited hydrogen. If you felt that the information that I had passed on to you is useful, please don't keep with you alone, share it with your friends too. Thank you very much for watching this video.